Hi everyone, welcome to my Math for Machine Learning series. My name is Kylie Ying and today we'll be talking about calculus, specifically derivatives. Derivatives are super important for machine learning because one big problem in ML is trying to find the maximum or the minimum of some reward function and trying to pick the model that might give you the maximum of that function. And so in order to do that, we have to use calculus. Today we'll be talking about calculus for machine learning. Now, the first part of a derivative, some of you guys probably don't even know what a derivative is. So for starters, we have to talk about something called slope, which you guys might be more familiar with. So slope of a line. And that might be something that you guys are a little bit more familiar with. So slope of a line, if you have, let's say, your axes like this, and you have a line that goes maybe like this, where each of these is 1 unit. I can't really see the dots. And each of these is 1 unit. And I'm asking you, what is the slope of this line? By slope, what we mean is we want to figure out how much this line increases per unit of x. And so, of course, this is the x-axis, this is the y-axis. So the slope is actually defined as rise over run, which is also the same as saying what is a change in y and what is a change in x. So I'm going to use this little triangle to signify change. So delta y over delta x. And this basically means change in y over change in x. What is a change in y? So the change in y might be, it's basically saying how much change in this axis do we get for some unit of change in this axis. So let's actually look at this line example that we have right here. Well, we know that this line is going to intersect our y-axis over here at x equals 0. So we know that this point here is 0 on the x-axis, 1 on the y-axis. And maybe, for example, this point over here looks like we go through that one. And this one over here is, it looks like 1, 2, 3, 4, 5, 6. 6 on the x-axis and 1, 2, 3, 4 on the y-axis. So in order to find the slope, what we're going to do is we're going to calculate the change in y. So how much difference is there between this value and this value? So delta y equals 4 minus 1, right? Because that's the change between here, which is effectively 3, over how much change in x? So that's the change between here and here, right? And this number is 6. So that's 6 minus 0. And we get 3 over 6, which equals 1/2. So the slope of this line that I just drew over here is 1/2. Basically, what we're saying by saying that the slope is 1/2 is every single time we go over 1 step on the x-axis, we are actually also going up 1 step on the y-axis. Not 1 step, half a step. So if we look at this line over here, we're going over 1 and then we're actually going up half. Every over 1, we're going up half. And that doesn't even have to be for like the ticks on the x-axis. You could even be here. As long as you're going over 1 unit on the x-axis, you're going up half a unit on the y-axis. Now let's take a look at some other examples. So if I had, for example, a line that looked like this. Well, here it actually looks like we get almost 2 up per over, right? We get 2 units of y for every unit of x. So this slope here is 2. Now in this video, because this is a really condensed version of calculus for machine learning, I don't really have that many examples that I can go through to show you guys because it's not a full course. However, if you guys are looking for a good in-depth resource, I highly recommend today's sponsor, Brilliant. Brilliant is where you can actually learn by doing, with thousands of interactive lessons in math, data science, programming, and AI. What's really awesome about Brilliant is that it's a site that's designed to teach you how to think. It's an interactive course where you're not just memorizing the material, you're actually playing around with the concepts, visualizing them, and doing exercises. Hands-on problem solving is actually a method that's proven to be 6 times more effective than just watching lectures. Brilliant has a giant library of math courses, so it's really perfect for learners of any level, whether you're just starting out in calculus or whether you're trying to learn some more advanced topics. Brilliant is just packed with core concepts, and they really focus on the essentials in these lessons. Best of all, you can try everything that Brilliant has to offer for free for 30 days. Visit brilliant.org/Kylie Ying or scan the QR code on screen. Or you can click the link in the description below. You'll also get 20% off an annual premium subscription. We could also have something like this. Now, what would the slope for that be? For every single time we go over 1, we're actually going down this time. We're going -1. So the slope of this line, so remember here we're doing the change in y divided by the change in x. So if this point over here is, okay, I didn't draw these axes that great, but let's say this is like 2, 1, and this here is 1, 1. Then our slope is going to be the change in y, which is, sorry, that should be 1, 2. Our slope here is 1 minus 2 over 2 minus 1, which is going to be equal to -1. So this slope is actually equal to -1. And any slope that goes downwards from left to right is going to be a negative slope. And also just a note here, I could have said 2 minus 1 over 1 minus 2. You just have to be consistent. If you're subtracting this y from this one, then you have to subtract this x from this one. Okay, you just have to be consistent with which value of x and y comes first. Now, what about a slope of 0? What does that look like? So if you have a slope of 0, that actually is just a straight line. That's flat. And that's because for any like increase in x, you're not going to get any change in y. And so that means that the slope is 0. Alternatively, what does an infinite slope look like? So that's actually just a vertical line. And the reason why it's a vertical line is because you don't have to go anywhere in x. X can be 0, and you're going to have an infinite change in y. Right? So kind of the gist here is that the steeper this line is, the bigger the slope is going to be. And the shallower the line is, then the closer to 0 that slope is going to be. Anything that goes up this way is going to be a positive slope, and anything that goes this way is going to be a negative slope. So that's a slope of a line. Now, what is a derivative? Let's talk about that. Okay. Now, in a derivative, I'm actually going to come up with a non-straight line this time. So let's say I have something that looks like that maybe. And say that I'm just drawing this random curve. So I'm actually going to choose a random point on this line. So let's say here. So what Newton and Leibniz said was actually there is also the concept of a slope on a non-linear curve. And that slope is actually just at that specific point, what is the slope? What is like the change, the rise over run at that given point? And so you might think, okay, well, how are we going to do that? Well, we can actually draw this tangent line here. And that becomes a straight line. Essentially what they're trying to argue is that the derivative at this specific point is actually equal to the slope of this line. It looks like it could be 3/5 or something, right? And then maybe, you know, the curve over here, let me do that in a different color. And then, like, for example, this point over here might have a slope that looks like this. And so that point, that derivative might be something like, looks kind of like -1, etc. And so you can actually do this for all of these points along this curve. And the function that ends up defining what the points are, that's going to be called our derivative. Well, that's where the mathematical definition of a derivative was born. Definition of a derivative. And in this definition of a derivative, basically what this is saying is, so if this function is function y, then we have dy over dx. That's one way to say, hey, this is the derivative of y. Or you could call this equal to y prime. That little tick is another way to do it. Or you could even have a little dot above your y, and that would be the first derivative. We'll talk about that later. That'll also mean the derivative. So all of these things are equal to the limit as h gets closer and closer and closer to 0. So I'll explain what all of this means. Let me write it down first. F of x plus h minus f of x divided by x plus h minus x. Okay, what does that even mean? So let's say I have some function, and this, I know I just called it y, but this function can also be written as f of x, right? That's just a different notation. I'm going to call this function f of x. And if it's, you know, this is 1, then this point here on this function is f of 1, right? And so if I take one step over, then over here it'll be f of 2. Understood? Now, what this function is this part here. Well, this is slope, right? It's a change in x, or sorry, this is slope. It's a change in y over some change in x. Now, what does all of this fancy stuff here mean? And where does the h come in? And what does all of that mean? Well, this is basically saying, okay, I'm going to choose some number to represent x, right? So let's say I choose this. That might be, it looks like 4.2, right? That's going to be my x. And so this basically means, okay, this is this value, the y value at x equals 4.2. And my x here is going to be 4.2. It looks like the y is somewhere around like 1.2. Now this h, this notation means h is going to get really, 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 really small. So if we said like, oh, h is 1, then now x plus h is just going to be 4.2 plus 1, so 5.2. But what we're saying is we're going to make h like super small. Like you can't even see it with your eyes small. Like if our x is here, then our x plus h is going to be right there. And like this tiny difference there that I can't even draw with this pen right now, like this difference here, this is going to be h. And so this here, this is x, and then this here, this is at x plus h. So it's just saying like we're going to take a tiny step, okay? That's this notation that I just erased. It's saying we're going to take a tiny, 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 tiny step. And that gets us to this next place. So that gets us to maybe right here. Okay, so here what I'm saying is like, let's make up numbers for x plus h, right? So x plus h, I'm going to step over tiny bit, so maybe 4.21. And then f of x plus h, well, that looks like it decreases a tiny bit, but not very much at all. So maybe like 1.1999 or something like that. And so now all of a sudden we have a way to calculate this, right? We have 1.19999 minus 1.2. That's negative 0.0001. Divide that by 0.01. And so that gives us a slope of somewhere close to 0. You know, so that there is not too big. But let's go back to this definition of the derivative. So if I have the limit as h goes to 0, f of x plus h minus f of x over x plus h. Well, some of these things actually cancel out. And so instead of, we have an x, but we just subtracted that x. So what this is saying is we're going to take that, like, the change in h, and we're just going to divide it by h, because h is our difference in x. So this is the definition of a derivative. And essentially, like, I want to drill this in, that what it's saying is take the tiniest step h in one direction, and that's going to get you another point on your function. Now, these 2 points, well, we're going to do exactly what we did up here for the slope. We're going to calculate the change in y and divide that by how big the step is, h, and that's going to give us the slope of the line approximately at that point. So that's the definition of a derivative. So if I have something like this, if I have a function here, so this is supposed to be, it's not perfect, but this is supposed to be f of x equals x squared. Okay, and let's say I'm trying to find the derivative at x equals 1. So what this is saying is, by the definition of the derivative, the derivative at 1 is going to be equal to 1, take some very small h. So let's say, let h equal 0.01. Okay, so what we're going to do is we're going to do this function at 1.01 minus this function at 1 divided by 0.01. And that's an approximation. And so we have 1.01 squared minus 1 squared divided by 0.01. If I use a calculator real quick to do that math, this derivative is actually 2.01 if I calculate it out this way. Okay, so this derivative is approximately 2, like this. This one here is even steeper. And this one here is less steep, but it's negative. And actually, at the very tip of this function, this slope here is actually going to be 0. And now, what does that look like if we plot all of these points? Well, we just said this one was equal to 2. This one here is 0. This one here is even steeper than that. I'm going to tell you guys right now that it's approximately 4. Now we have a function that looks like this. And that kind of looks like a line. Okay, so this red line here is f prime of x, whereas this black line here is f of x. So now what we can actually say is that this f prime of x, this red line, is the derivative of this black line. And you might say, okay, but it looks like this, I thought we were doing, the slope of the line. It looks like it could be the derivative of only a single point on this line. So Kylie, why are you telling us that this is the derivative when it's not the slope at the line? Well, I'm saying that this is the derivative because it's the function where if you match up these x values, so if you say x equals 1, then the derivative at f of x equals 1. So the derivative along this line at this point is actually going to be this value. So what this is saying is that the slope here is equal to 2. And the slope here, that more steep one, is actually going to be equal to 4. And the slope here is equal to 0. And the slope here is going to be equal to whatever this value is. Looks like around -1. So this red line, it's providing the slope at every single point along the black line. And that is exactly what a derivative is. Okay, now how do you find that red line? How do you find the derivative? It's not really feasible to use the definition of derivative on everything, right? If we have some form of a function, f of x, that takes the value of like to some x to the exponent, let's call the exponent a, okay? Then the derivative of that function is going to be in the form of a times x to the a minus 1 power. Okay, and that basically means that, for example, if my f of x is x squared, then the derivative of f of x is 2x. If I have some value in front of that, let's say it's x to the a power times b, well, that b actually stays. So here, this is all multiplied by b. So that means if I had like 5x squared as my function, then now this becomes 10x as the derivative. And if the value is just, let's go through a few other examples. I'll have f of x up here and then the corresponding f prime of x below that. So we just said 5x squared. So using this formula, which I'm actually going to rewrite here, a times b times x to the a minus 1 power. By that formula, well, what is a? A is 2, b is 5, so a times b is 10, x to the 2 minus 1, so that's just the first power, so it's just itself. What about, actually let's do this, 10x. What is the derivative of that? Well, x to the 1, if a is 1, 1 minus 1 is 0, and anything to the 0 power is 1. This derivative is just 10. And we can do this with some crazy exponents. So if we say like 7 times x to the 30th power, well, we can actually find the derivative of that. We can say this is, okay, 30 times 7, 210, x to the 29th power. And that would be your derivative. And what's really cool is if I actually erase these and make these plus signs instead. So let's say my function is all of this. Well, this down here, well, that's my derivative of that function. We can actually just add the derivatives of each piece together. In machine learning, we have this concept called optimization. And what that means is you might have some function that looks like this, and it keeps going on. And basically, what f of x is, this is your reward function, f of x. And basically this is like a user, like I've told my computer, hey, here's f of x, and this is how much like reward, so you can imagine whether it's money or whether it's, so you can think of it as like money or points or Dave & Buster's tickets, whatever. This is a function that I'm telling my computer, hey, every single time, you know, if x equals 10 over here, the amount of reward that I'm getting for that value that I put in is this number on that function. And maybe here at x equals -10, let's say x equals -10 is over here. I don't have axes here, so I can say wherever it is. And now I'm saying, oh, actually the reward at x equals 10 is higher, right, than the reward at x equals -10. So this is x equals 10, this is -10. X equals 10 is clearly higher than the other. Well, that's not enough for us, right? We actually want to know where is the top of this function. Like we want to know where is the maximum of that. And that's where optimization comes in, because we want to know this part up here. But do we notice anything special about that derivative? Do we notice maybe that that derivative at that point, well, hey, that kind of looks like it's 0. Similarly, if we have a function that looks like this might be something called a loss function. And I'm going to name that f of x again. And this means, okay, how much do we have to, like, how much are we losing by, you know, this specific value, x equals 5? Like, this is our loss. And obviously we want to minimize our loss, so we actually want this value down here, which again, you might notice, that's when the derivative is 0. And now how do we solve for that? Well, we just said that for something exponential, so like for x squared, the derivative of that, so if f of x equals x squared, the derivative f prime of x is going to be equal to x, 2x, going to be equal to 2x, right? And now we're just going to say, hey, where is that 0? Well, solve for x. It's going to be x equals 0. But, you know, maybe you have f of x equals x squared plus 3x. Now, f prime of x for that is going to be equal to 2x plus 3, right? So 2x plus 3, we're going to set that equal to 0. And that's essentially going to give us the x value of, you know, where the derivative, where this is flat, which is going to be a maximum or a minimum in our case here. And so here, x is going to be equal to -3/2. Now, we have to be really careful, because what if we have a function that looks something like that? Well, there's actually a point here where that derivative is going to be flat. But that's not a minimum or a maximum. So we have to be careful. Just because something is equal, the derivative is equal to 0, doesn't mean it's always going to be the minimum or the maximum. Another example is, what if we have our reward or our loss function look something like this, right? Well, I mean, let's say that goes back down, but all of these points along here are going to have a derivative of 0. But there can only really be one maximum or one minimum. Like, these two are both maximum, but this might be like the maximum of the whole thing. And same here, these might be minima. But this function goes all the way down. It keeps going. So maybe there is no minimum. These are good questions to keep in mind. That's what I have to tell you guys about derivatives for today. Remember that what the derivative represents is just the slope at a specific point on a line.